Imagine muddy water invading Paris. Imagine Hôtel de Ville, Place de la Concorde, or the Louvre inundated. These images are not those of a disaster movie. They are a projection of what could happen in 10 years, 1 year, or perhaps even in a few weeks. A major flood of the Seine in Paris.
We know that at any rate, whatever happens, these high waters will occur and will cause problems. And the crucial question is ensuring that it doesn't end in a catastrophic scenario.
Because this kind of scenario has already happened in 1910. The centenary flood, a huge rise in the Seine that occurs on average once every 100 years and whose return is inevitable. With a paralyzed capital, public transport that stops operating for several months, thousands evacuated, a widespread blackout for millions of people. Since 1910, Paris has tamed the Seine. Paris has protected itself, but also made itself more fragile, with an underground like Swiss cheese, full of networks, transport systems, and parking lots. Like all the major cities in the world, the French capital has spread into the suburbs with millions of additional inhabitants.
It would be an extremely complex event to manage, particularly due to the thousands of people to evacuate.
To confront the challenge, every day dozens of experts are working to plan for the rising water, to reduce the power of the river and limit the destruction. But while the science is progressing, climate change is reshuffling the deck. Everywhere on the planet, natural disasters are increasingly devastating. In Paris, the tension has gone up a notch.
The 1910 flooding of the Seine has become an average flood, and we are now asked to work much more on extreme floods that would greatly surpass what they had in 1910.
Now, imagine what would have to be done that day. How do we prepare for what is increasingly likely, but never certain? The Seine, the most beautiful thoroughfare in Paris, flanked by the city's most prestigious monuments. But it is far from being a tranquil river. It can transform itself into an absolute nightmare for Parisians. In 1910, an exceptional flood paralyzed the capital for several weeks. The water attained a record high, transforming the streets into rivers and making life impossible.
It's quite mad that the images we have of Paris during the flood make it look like Venice. There are ladies in long dresses strolling along flooded canals. First of all, we forget that in these streets it smelt really bad. There was refuse, there were holes, so there was the risk of roadways collapsing. We forget that people were cold, that people were hungry, and it's true that for the first time people were being photographed. They weren't used to seeing cameras. They're almost posing. These photos don't reflect the difficulty that these people experienced at all.
Avoiding another 1910, immediately after the disaster, the government tackled the issue. Its first mission was quite obvious. How could the Seine be regulated? How could they prevent the water rising so high?
As with every major flood in this country, afterwards there was a commission of engineers who gave feedback about what had happened, then gave advice on improving and ensuring that it wouldn't happen again, or less often, or that the damage would be minimized.
Over the years, they destroyed docks, widened arches, and dug out the riverbed to improve the flow of the Seine.
At the same rate of flow, all of these renovations enabled a level of flooding like that of 1910 to be reduced by around 30 centimeters mechanically.
But these 30 centimeters gained were insufficient. In the following decades, other floods threatened the capital in turn. They had to strike a harder blow. "200 kilometers from Paris, the Lac d'Orient is a place for Sunday strolls, a leisure center. This huge body of water didn't exist 100 years ago. It has two missions. In summer, when the river level drops, it releases water to allow for navigation. for drinking water production or for the cooling of the nuclear power plant of Nogent-sur-Seine. In winter, however, when the Seine is high, it retains water to avoid flooding and protect the region of Île-de-France. The lake is located on what is known as the catchment of the Seine, that is, the series of rivers that feed their water into the river. To retain the water in the event of flooding, besides the Lac d'Orient, 4 other reservoir lakes have been built for the largest of the river's tributaries. Pansière in the Morvan region to slow down the Yonne, Der-Chantecoq that regulates the Marne, and Temple and Amance that keep the Aube in check. All of this was not done with the click of the fingers. Farmers had to be expropriated and villages swamped to gain just a few precious centimeters.
The cumulative effect of capping peak flood levels on these 4 lakes would allow, for a flood like 1910, around 60 to 70 centimeters to be alleviated from Paris. Obviously, if it occurred in the same way in the month of January, at a time when it is almost completely empty.
These 70 centimeters gained thanks to the Great Lakes, added to the 30 centimeters from the renovations, have improved the flow of the river, allowing the water level to be reduced by 1 meter in the event of a flood similar to that of 1910. More than a century later, the capital was thus shielded from a repeat of the 1-in-100-year flood.
It's true that there's this absolute confidence, and many people tell me anyway the river can no longer overflow. The river is controlled, mastered, there won't be any more floods or damage. In the end, these kind of events will go smoothly. We'll know how to cope with them.
But the system is not infallible. What happens if it rains in the spring and the lakes are already full? And what happens when it rains between the lakes and Paris? This is exactly what happened in 2016.
In 2016, the rain came down upstream of the lakes, so physically we don't know how to send water back upwards. Firstly, the lakes were virtually full at that time of year, and I believe that the efficacy of our lakes on that flooding in Paris was around 5 centimeters.
Just 5 centimeters less in Paris retained by the lakes in 2016. This flood confirmed it. These reservoir lakes are not enough. But they should soon receive a significant boost. A 120 kilometers away, a huge construction site is just getting underway. In La Bassée village, in the Seine-et-Marne, it will be the most recent addition to the series of Great Lakes.
Do you think it's coming along nicely?
Yes, it's starting to look like a storage bay.
Unlike its older siblings, the village is located much closer to Paris, just before the junction with the Yonne. It will therefore protect the capital much better. But it is also a very different construction site. It is no longer a matter of flooding villages. The lake is being created over existing artificial swamps, and here, the water is only stored for several days. It won't be a real lake, but a series of 10 basins that will be filled by pumps just until the floods are over.
We are right here in the middle of the first basin, so the area of the dam will be all around us, and dikes will be constructed all around us. And this will be a site for when a heavy flood in the Seine fills up to a height of 2 meters. Here, for instance, we will have 2 meters of water above us when the basin is in use. Then, once the flood is past, we will evacuate the entire site, and it will recover its traditional uses, the ways in which it was used prior to the renovations.
In the event of a new 100-year flood, the village could allow another 40 centimeters to be gained in Paris's water level. Construction is scheduled to end in 2030. But will it be too late? With global warming, the risks of a flood like that of 1910 are very real and might occur at any time. July 2021. For the first time in midsummer, colossal amounts of rain fell on the north of Europe. In Belgium and Germany, floods caused dozens of deaths. Meteorologists were caught short.
All of the historical records were beaten with this event, and so there was nothing comparable in past chronicles. And that also shows that, up until now, flood prevention has often been organized by studying past flooding events. Of course, we must continue to do that, but we must also integrate new types of events that might occur.
At the National Weather Center, a whole sector is now assigned to climate change. A vast study has been launched about the 50 years to come. And perhaps counterintuitively, warming does not mean less rain, just the opposite.
In a hotter climate, there will be more water vapor in the atmosphere, so we should have more precipitation. This excess of humidity that is in the atmosphere will not be distributed homogeneously over all areas of the planet. Some areas will have more rainfall, and this is notably the case for Northern Europe, whereas, for instance, the Mediterranean basin will have less.
For the catchment area of the Seine, this rise in temperatures should be expressed by two phenomena: drier summers, but also more extreme rain events capable of causing floods. In winter, an overall higher rainfall volume with direct consequences on river flow levels. Irrespective of the season, the scenarios therefore all converge towards the same conclusions. The centenary flood becomes a bit more likely every day. So how do we confront the threat? How do we prevent water from spreading everywhere? How do we protect Paris and its architectural treasures, like the Louvre? This morning, the famous museum is testing a new anti-flood system of protection.
We'll have to go back over each of the sacks to distribute the sand evenly, so we're ready if it's triggered.
Located on the banks of the Seine, the Louvre is particularly vulnerable. Based on recent expertise, the water could overflow via this low point on the quay and infiltrate the museum's basements. This barrier of huge sandbags should slow the water down.
We time how long it takes to put a certain line of big bags in place. So we time it big bag by big bag. And then we average out the whole line to have a better understanding of the time necessary to install 172 meters.
This morning, it took 3 hours to set up the barrier. For the museum, it is crucial to constantly refine these protections. They must prevent the water from crossing the road and reaching the Islamic art rooms or Greek antiquities located on the ground floor and basement of the palace. But here, the enemy can attack from anywhere.
Nowadays, in the event of a massive influx of water, we have huge difficulties identifying precisely by which point the water will enter. Today, the museum basements are a massive Swiss cheese. There are many cables that pass everywhere. There are a lot of technical networks, doors all over the place too. All of that means we don't know where the water will come from and in which direction it will circulate.
It was in June 2016 that the museum became brutally aware of its fragility. At the Louvre, the alarm was raised. A flood took Parisians by surprise in midsummer. The water reached 6 meters at the reference point of the Pont d'Austerlitz. The museum closed its doors and activated its anti-flood plan. Hundreds of artworks kept in storerooms were urgently brought to the upper floors. In the end, the Seine did not rise any higher, but it was a close call. because despite all its efforts, the staff of the Louvre were only able to evacuate a quarter of the artworks under threat. 120,000 works could have been damaged if the water had risen higher. They were a hair's breadth from disaster. Since then, all of the storerooms have been emptied and transferred. Thousands of artworks have been shifted to a new annex of the museum 200 kilometers north of Paris. The Louvre collections are safe. Paris has a globally unique heritage, but the main concern is Parisians. Including the suburbs, there are over 12 million inhabitants. A huge anthill dependent on a vast transport network, the metro. How is the company preparing itself?
As a reminder, the goal is for us all to acquire experience, because the 1910 flood will happen one day. Every year there's a 1% chance that it happens.
This morning, employees from the Parisian Metro technical crew had a rehearsal on the Place des Invalides that was completely covered in water in 1910 and that would flood again with a 100-year event. The apparatus is impressive. They came with breeze blocks and cement mixers. The first phase of the plan consists of sealing off 80 points on the networks, metro entrances, but also air vents, as in today's exercise. And that's just the beginning.
There are nearly 429 element areas that must be protected. These are places where, if there is a flood, near the Seine as we see here, there will be risks of water penetration. So edifications are put in place, anti-flood protections that will prevent the water penetrating the network if the Seine overflows and avoid disastrous damage.
The 1910 flood highlighted the network's fragility. Not only did the water engulf several stations, but it spread via the tunnels and flooded the neighborhood of the Saint-Lazare train station several hundreds of meters from the Seine. Most of these men are not masons, but metro employees, who were trained prior to the big day. During the exercise, every detail is checked. So the manager takes note in a notebook, in the traditional manner, because on the day of the flood, telephones might not work. A few meters away, a second group mounts cofferdams, an aluminum protection. In maximum alert phase, the Parisian Metro Technical Coordination deploys 800 people to block all of the air vents and at-risk station entrances within a few hours. But water is a devious enemy, and even with such an armada, the engineers have discovered a few faults.
There are 429 element areas that will be raised to the surface. With this in mind, we need to prevent eventual weaknesses of one of the areas, whether that be related to vandalism or to a vehicle thrown against a protection that might hinder its resistance, even if the barrier is put up on time, and thus cause total or partial spread of the flood waters within the network.
What the Parisian Metro coordinator wants to avoid is what happened in New York during Hurricane Sandy in 2012 or Hurricane Ida in 2021. "3 o'clock in the morning, Pyramide Station. To prevent water flooding the interior of the network, the Metro employees have set up their first anti-flood gate overnight, this time directly in the Metro. Pyramide Station is on line 14, the most sensitive of all. The most recently constructed line, it is the deepest, fully automated, and runs alongside the Seine. It notably passes through the 12th district, where the water could rise to a very high level. If the protections give way at the Cours Saint-Emilion station, for instance, water could flood the entire line. At Pyramide, it could then go up 2 levels via metro stairwells, that is, over 20 meters high, and unfurl onto line 7. For 2 nights now, about 20 people have put these 2 400-kilo gates in place that must prevent the water from transferring to a connecting line.
Our goal now is to avoid resurgences happening all over the place if the water gets in somewhere. That would damage a lot of the network, even if there's only been 1 penetration point, for instance. So that is what we're trying to do by setting up these secondary partition gates that create a second layer of protection of our infrastructure.
But the metro is not the only network that allows the water to spread very quickly. There is another, even bigger one in the entrails of Paris: the sewers.
And now, is it smelly or not? No? A little bit?
Their role is specifically to help water circulate, and not the cleanest of waters.
Here we have the connector. This is where the wastewater circulates, in this conduit here, which is the basin of the connector.
In theory, this wastewater is not cast directly back into the Seine. It is sent back to water treatment plants that filter it before returning it to the river. But in Paris, the sewers have a special feature that complicates the situation in the event of floods. Besides wastewater, they must absorb all of the rainwater within the same network. When it rains a lot, the sewers are saturated. So that they don't overflow, they are forced to discharge into stormwater spillways. These forks that lead directly to the Seine empty a combination of rainwater and wastewater into the river. But in the event of a flood, the stormwater spillways become a hazard because the water of the Seine could go in the opposite direction.
If we do not open the stormwater spillways, the wastewater will first start entering the cellars, which may not be watertight, and if the water level continues to rise, it will even flow over the roadway, disactivating the sewer buffer zones, with disastrous consequences for the environment and the population.
One solution remains: batten down the hatches. Prevent the water of the Seine from entering the sewers by activating about 40 floodgates, like this one.
When the Seine rises, the floodgate will start to close to stay above the level of the Seine. When the Seine is 20 centimeters under the vault, the floodgate is completely sealed, which means that the Seine can't enter, but we can no longer evacuate wastewater either.
So the sewers can be protected from flooding by closing the floodgates. But if it rains at the same time, then the network will very quickly be engulfed and the sewers will overflow. So we must avoid the rainwater joining the network. However, in Paris, if we exclude the Bois de Boulogne and Vincennes, which are peripheral woods, 80% of the ground is watertight. Roads, pavements, housing. All of this water will therefore run off into the sewers without penetrating the soil. To reverse the trend, researchers are working on the concept of a sponge city, a city that absorbs water. In the middle of the Bois de Vincennes, to the east of Paris, this little corner of the garden is photographed by drone once a month. 2 plots of land side by side, which are in fact a mini laboratory flanked by sensors.
So here we have radiating infrared sensors operating directly and indirectly, and basically all of the sensors are actually distributed everywhere at various depths. And here we have the cables that emerge and connect with the electrical cabinet that will centralize the data.
The sun's rays, the evaporation of the water, the amount of rain, everything is scrutinized and analyzed. The 2 plots are almost identical, but the same plants, the same garden soil, the kind usually found in the city. One thing distinguishes them:
There is just one difference between these two plots. It's the way they're drained at the garden level. In each garden, there is 1.5 metres of garden soil and 50 centimetres of what we call the reserve, which is actually just a kind of rocky bed. We fill that part with rocks, and since they're rocks, there is more space between them, meaning that we can retain more water.
In the first garden, the water that rises up to the rocks when it rains is immediately evacuated by a low pipe towards the sewers. In the second garden, however, the low pipe is closed. The only way for the water to evacuate is by evapotranspiration, that is, plants' ability to absorb water and restore it to the atmosphere. It is this ability that the experiment is measuring.
Today, the whole policy of rainfall management is about managing the rainwater as closely as possible to where it lands, at its source, and as much as possible what we call nature-based solutions. The idea is not to send it very far, not to let it flow, and if you do, it can go for a few metres, but it mustn't go for 300 metres. It's about recovering the most natural path as well.
The experiment of the garden laboratory is only in the early phases, but the first results are promising. This program belongs to a broader project launched by the City Council, the Paris Rain Plan. Since 2018, this new way of approaching water is even a statutory obligation. Every neighborhood must now retain a certain amount of rainwater where it falls. In the north of Paris, where the ground is not suitable for absorption, the obligation is only 4 millimeters per 24 hours. However, near the Seine, between 8 and 12 millimeters of rainwater must be conserved.
8 millilitres of rainfall in 24 hours represents just this height. Basically, this amount of water fell on Paris within 24 hours. If you add all this rain over Paris, between 0 and 8 millilitres over the whole year, in the end, the total volume that represents is 80% of annual rainfall.
Obviously, any new building permit must integrate this constraint. In this avenue in the 12th district, the sidewalks are being rebuilt with no borders around trees to allow the water to flow towards the soil directly when it rains. A bit further on, this street no longer allows any rain into the sewers. The paving stones let most of the water infiltrate into the ground.
Here there's still a good quantity of water, so we see there's a small proportion that still flows because this is the equivalent of a good dose of rain.
The excess runs onto a gravel bed under the roadway and will seep into the earth without ever getting into the sewers.
We are going to make Paris 100% a sponge. We won't make everything permeable. There will still be roads, but the question is how to build the city so that non-absorptive surfaces run towards absorptive ones.
But in the event of a major flood, the principle of the sponge city will not be enough. With its modernization, Paris, like all the major metropolises of the planet, has become fragile. The city is now more vulnerable than ever.
Today we have 7 floors, 7 to 8 floors that are built under the feet of Parisians. All of the technical networks travel through these basement levels. The metro, electricity, gas, heating, and telephone wires that currently serve our daily lives. Around 5 million people will have basic services interrupted. So that means a very widespread shutdown.
According to experts, the first network to go down would be heating. The last would be drinking water. But the most crucial of all, the one on which nearly all the others depend, is the electrical network.
Electricity is extremely important because the networks are interdependent. If you don't have electricity, you can't operate the metro system, for example. You can't run telecommunication networks, you can't run water. So in order for the networks to function, we need electricity.
But electricity is like anything. They will try to cut it as a preventative measure to protect their installations from the water. So we might find that 3 or 4 days before we reach the peak, there are suddenly whole zones without electricity.
The most sensitive area of Paris is in the heart of wealthy neighborhoods, at the Alma intersection. Here, underground, there is an area under heavy surveillance. Today, a flooding response coordinator for a French electricity network has come to inspect this substation that has been completely restructured.
Hello, how are you?
It powers 110,000 homes, and its proximity with the river makes it the most vulnerable if the Seine overflows. In the Paris region, electricity is produced by nuclear, thermal, or hydraulic power plants far from the capital, in places that have no flood risk. Electric motorways of 400,000 volts lead to transformers located in the suburbs far from the Seine. But then, the 225,000 volts circulate underneath Paris in big cables, which sustain 36 transformation substations, sometimes threatened by flooding, such as that of Alma. It is there that the final transformation of the current is undertaken before being directed towards local substations, then on to homes. The core is 2 levels down. That is where, behind a watertight door, the imposing transformer is located.
Here's the transformer. As I was saying, it's brand new.
Well protected, it is preserved from any river floods.
It's quite big. It weighs several tons and is full of oil, so it's very heavy.
So this is where the 225,000 volt cables come to.
The trouble starts on the next floor down, the 3rd basement level, 12 meters below ground. It is the starting point for all the cables that will power the neighborhood substations.
I'll show you the pump and the first aqua barriers. These are all the cables that will go into the street to provide power to customers.
The sensitive points are not the cables themselves, but the connections that must stay out of the water. So in the event of overflow from the river, the water can plummet through the galleries or via ventilation shafts. The room is therefore compartmentalized.
So this barrier here, which has to be lifted, is to keep the water inside, right?
I'll show you. Let's put the plates like this. We'll tighten it with butterfly discs. We'll tighten it there.
Okay.
That way, if the water rises on this side, we'll be dry. And the water that'll rise on this side, you'll see over there. We have a pump that allows us to re-inject it into the Seine.
As soon as the water reaches a concerning level, pumps start working to cast the water back into the Seine. But the most threatened floor is the 4th and final basement level, located 15 meters down.
What we can see is that the equipment used to be kept at ground level. You see through the fences? You can see it was on the floor and was removed, so we could gain 2 meters of height. Just in case, so more water can come in here without a problem.
Before, the most sensitive installations, such as the transformer, were found here. Today, there's almost nothing left. Yet, if this floor is under threat, it is not so much due to the flooding of the Seine as it is to a much more pernicious danger.
Here you can see that the water infiltrated the substations. So, now we check that in times of flood, the water will not flow in here.
Here, the point of weakness is infiltration via the phreatic zone. A danger that could, in the event of flooding, become the major issue for the capital's entire substrata. When the water rising from this layer adds to the overflow of the river, the situation can become uncontrollable. Usually, the phreatic zones are pockets of water in balance with the Seine. They flow into it slowly via underground pathways when the ground fills up with water after rain. But the rising waters of the river can provoke a phenomenon of reflux. The water from the Seine flows massively into these zones, which can no longer drain, and their level rises.
We must imagine this flood is like a piece of theatre where everything plays out backstage. What you see is very, very different from the reality of the flood, because most of it is happening underground. A phreatic zone imbibes everything. You can't stop it like a coffee filter. You can't staunch the progress of water. You can lay sandbags, create dikes, build walls on the surface. This controls it a bit. As for the phreatic zone, there's nothing we can do.
Nevertheless, surveillance of the phreatic zones exists. The capital's underground levels are therefore gridded with dozens of piezometers, a tool that allows the height of the zone to be measured. Some are near the Seine, others, like this one, must go down almost 36 meters to find the water of a zone. On this hill in Paris, however, there is no risk of flooding, but the measuring instrument participates in the overall surveillance of the substrata.
Please write this down. So the depth is 3670. That's good. The temperature is 15 degrees.
15?
Okay, so that's fine. This point during floods will not be impacted much, but it provides information on how the water circulates in the zones on the scale of inner Paris. So we need data points all over the place to be able to understand how it works, how the water flows.
Ok, super.
But where is this zone? What does it look like? Is it at once nearly everywhere and almost invisible? To have a chance of meeting this formidable enemy, we must sink deep into the Parisian underground, into the galleries of former quarries. For instance, it shows through in this pit created 2 centuries ago by monks.
People often think that a phreatic zone is an underground lake or river, but no, it's water that's inside rock. So usually, technically, you can't see it. A phreatic zone is a bit like water in a sponge, or for instance, when you dig the sand at the beach and after a while you hit water, seawater. It's the same principle.
Thanks to their data, the engineers from the quarries are constantly aware of the water level. But predicting whether the zone will rise and by how much is much more difficult.
Currently, when there is a flood period, we monitor the level to inform Parisians of potential flooding of the substrata. But it's more complicated to make predictions because there are many parameters we're unaware of, such as pumps.
Pumps. They began in the early 20th century with the conquest of the substrata. Paris sometimes has up to 7 levels underground filled with parking lots, metros, galleries that thwart the natural movements of the phreatic zones. To tame it, the builders used pumps that cast the water from the phreatic zone into the sewers or the Seine. Hundreds of them are operating constantly in Paris. This concerns the Parisian metro especially. A large part of its network is located at the level of phreatic zones. It has 270 pumps like this one, crucial in all seasons. Here, for instance, is the water from the phreatic zone permanently evacuated by the pump over part of Line 8. Without it, the line would immediately be flooded. The pumps are a few meters away from the tracks, protected by a watertight door to continue to operate even in the event of flooding. To protect its network, the Parisian Metro Coordination Unit powers the pump using a dual electrical circuit that limits the risk of outages. It also equips this substation with sensors that alert it if the rate of flow suddenly increases. But the phreatic zones remain an area for concern. What would happen if, in spite of everything, the pumps stopped? Researchers from the top school of engineering have been working on this question since 2016.
We created a digital model of the Parisian region by referencing all of the pumps. So now, we have surveyed over 300 pumps that annually sample 19,000 million cubic meters in the Parisian substrata, mainly to preserve infrastructure.
Next, the researchers identified the pumps that should stop with electrical faults due to flooding. These are all the green dots that have turned red. The immediate consequence is that the water from the phreatic zones starts rising. In light blue, the water is no more than 12 meters from the surface, that is, in the deepest parking lots. In a deeper blue, it is less than 8 meters. In dark blue, the water from the zones is under 4 meters. In the 12th or 15th districts near the Seine, the rise of the zones adds to the overflow from the river and makes the situation even harder. But the study also revealed a few more unexpected consequences. The Forum des Halles on the right bank, this underground mall in the heart of Paris, is far from the Seine. It shouldn't be affected by the river bursting its banks, but the threat comes from underground.
In the event that all the pumps stopped, well, we observe water levels that are between 0 and -4 meters underground. So possibly a flood in the lower levels of the Forum.
Water that would rise to 4 meters below the surface. That is, in fact, all of the shops that would be flooded. In some neighborhoods, the water from phreatic zones could even rise to the surface and accentuate the floods provoked by the flooded river. Water is by nature an element that is uncontrollable. While Paris has become aware of this challenge, scientists and authorities know that it will be difficult to prevent the city from partial flooding. How can we reduce the risks for all of these urban areas that know they are threatened by floods? Do we need to come up with new architectural solutions to make the city resilient? In France, there is a place where this idea has been put into application. This neighborhood of Romorantin in the Loire-et-Cher once belonged to the Matra factory. In 2007, architect Éric Daniel Lacombe was given the task of restoring it. But the neighborhood runs alongside a little river, the Souldre, which has proven to be rather restless. So the local council imposed two constraints: no housing less than 1.50 meters from the ground, and no more than 20% of the land could be built on to allow the water to flow in the event of flooding. The architect thus designed the new neighborhood as a place that might be flooded at any time.
We are working on what we call natural regulations, meaning that the water enters the neighborhoods. The water flows through neighborhoods. The water loses its force as it passes, and the water returns to the water. The real issue is allowing the water to return to the water and not remain blocked or degraded by the houses. The whole neighborhood is built in the direction of the current. There is a straight road and a road curved like the river, and between the two, there is still water flowing in the direction of the current. That's how, in the direction of the current, you rip out fewer trees, you sweep away fewer cars, you do less damage, and there is less kinetic energy.
The houses are arranged around a big garden that transforms itself into a temporary tributary when the river overflows. In the middle, we find a few traps for slowing the water down.
So here we are on a catchment basin. That is a place where the water will fall as though into a hole, lose a bit of energy, calm down, before returning to the river behind me.
The neighborhood is built in levels. The road is raised by 75 centimeters, the pavement by 1 meter, and the houses are raised by the statutory 1.5 meters. In 2016, when the Souldre lifted off its bed, a huge flood submerged the city center. The new neighborhood was also flooded, but it was still possible to live there, and the water went down much faster than elsewhere.
The water rose up to 1.45 meters, that is 5 centimeters below the first residential floors. And there was no damage. Why? Because firstly, the water rose to 1.45 meters, but above all it dropped again, through gravity, into the river. And that is what I worked so hard on. There are leveling systems that allow the water to rise in one direction but go back down in the other. And so it went back down into the river in less than 48 hours. That's what allowed the neighborhood to avoid damage, while the water remained blocked in other neighborhoods on the left bank, on the other side, on the opposite island, for 3 weeks.
Since then, Romorantin has become a reference case, and the architect is advising many elected officials in the Parisian region. But the example of the Matra neighborhood, with a great deal left up to nature, would not be easy to reproduce.
Near the Seine and in very big urban sites, you are working in Paris, where the land is worth a fortune. I think that market forces can be a barrier to natural regulation. But that is what is known as societal choices.
In the meantime, it's the Seine that dictates its law. If Paris has to endure its rage, it would take at least 3 months to recover normal life. The water, electricity, and transport networks would take time to be repaired, possibly even several years. Because despite all the research, all the protections, scientists have only one certainty. This flood will never be exactly the one they expect.
I'd say that we must prepare people to be surprised. It is really the notion in which this phenomenon, we think we know it, in part. But in the end, we realize that with the phenomena that occurred in 2016, 2018, we have always been surprised by some of the things that happened.
Unfortunately, all of the solutions that we can develop today will attenuate these phenomena, but could never prevent them. We will also no doubt have other floods that will come, as I was saying, to highlight the flaws in our protective systems or weaken them a bit. So we must be prepared for these issues.
So now, we need to train people to confront phenomena that are very violent, that truly call into question their organization, and really get them used to being much more reactive to them.
And rather than being a spectator to what might happen, we must also transform. Learning to live with the floods means becoming an actor within this system, being yourself, and capable of rising to the challenge on your own scale.